So the goal is to do Kummer extensions today. I don't know if you see it so well, but Kummer extensions and then our function fields. This is maybe, I don't know, probably each of them is like an hour and something. We'll see. So what are Kummer extensions? So in item 1, there is a Galois review, which I don't need, but it's nice to have. I mean, I'm not going to do it now. That tells you, that kind of characterize what are the finite cyclic extensions, how they look like. It's something that you sometimes do in Galois and sometimes you don't, depending on time. I'm not going to need that, but I thought it would be nice to have it here. Last time, previous Tomer, Shir, did it in recitation, and I mean, I'm not going to use any of the results there, but I think it's nice to kind of have a recap on that, so you can look at it if you want, but I'm not going to do that. But it's quite, it's not so trivial Galois. Like it's like the end of the course Galois, kind of. But yeah, I'm not going to need that. So, but if you want, you can look at it. The first thing I want to start with, I don't want to talk about Kummer extension, but I do need one little claim that is related to the recap and is useful here. So let me start with that. So, you can ask what happens when you do a function field extension when the extension is of constants. So what do I mean? So let's say that L over K is a finite separable extension, like F4 and F8, F4 and F16. F8 doesn't extend F4. And let's say that you have a function field E over K. So you have a function field with constants coming from the little field, K. And what I want to do is to consider an extension of E over K, but it's not a very interesting extension. What I'm going to do is I'm going to look at the extension F over L, where F is just E composed with L, like the compositum of EL, like the smallest field containing both E and L. So really what I did was I didn't kind of add functions. E is there, L is there, but nothing else is there. So what I really did was to have the same functions, like the same transcendental element. There is no like extra Y, only X, so to speak. But the constants now are not just K, they are L. Like the function field extended now to L. So maybe you have like some curve that you like, y squared equal x cubed minus x, and you walked over F15. No, I can do it. Over F5. Now you can walk over F25. You can extend it to F25. 15 squared is hard. It's like 225. I'm going to, okay. So you can ask what happens with that, and you can ask who cares? Like, why don't you just analyze it from the get-going over F25? So actually, it's kind of weird. I mean, you don't care. For coding theory purposes, you don't care at all. But in order to prove the Riemann hypothesis over function fields, you really care about that. And that, I mean, the idea of understanding how the same function field behaves as you kind of add more constants, but the same code, same curve, but over larger and larger fields, is kind of fixing the problem that you have in which the constant field is not algebraically closed. So you're kind of looking at all algebraic extensions of the same function field in a sense, right? It allows you, F5 is not closed, but sometimes things happen in F25 that didn't happen in F5. So if you kind of understand all of them at once and kind of form a generating function that captures all of this together, then that will help you prove that's the basic. That's the idea of proving. That's one of the ideas you need in order to prove the Riemann hypothesis. So there is a whole unit about constant field extensions, which I'm not doing here. I'm going to do what I need from it next time. And it's useful for the proof of the Riemann hypothesis. But the bottom line is that nothing changes. That's kind of the bottom line. So the ramification index is the same, the genus is the same, everything's the same. And this lemma is just the one thing I kind of took from that which I need. So this lemma tells you that, if you have f e over k, and then you only extend e by adding L to it, so f is now e over L. And then indeed, if you take any little prime divisor, like prime divisor in e over k, and you look at an extension of it in f over L now, because you extended f to be e over L, and therefore the constants are coming from L, then the ramification is just 1. Like nothing changes. It's all kind of the same, essentially. But the proof is not trivial. Yes. Yeah, exactly. So, right. Well, F5 or F25. F5 and F7 are, they are different. Like the factors could be very different. But Nothing changes because this is like geometry and not arithmetic. This is a geometric property. Like, I don't know. It's hard to say that. But it's like more geometric than algebraic, than arithmetic, than the field dependent. It does depend on the field. Like F5 and F7 is different, so it's not accurate what I'm saying. But it doesn't kind of see extensions of the same field. Except for the things they do, like Riemann-Roch spaces will grow a little bit. But anyhow, don't worry about that. We'll see. So how do you prove that? I mean, it sounds easy. I don't know. I mean, if it stays the same, but actually it's not so easy. And it's a very easy proof now, but we have to use what I stated before. So first of all, in order to prove that, note that L is always can be extended using is kind of a simple extension of K. Right? These are finite extensions. They are separable. There is always a primitive element. So let's write L as K times alpha, K of alpha. And let's denote by phi the minimal polynomial of alpha over K. Okay, so it's an irreducible polynomial over K. It's used to extend K to L. But if you remember at some point, I don't remember at which point, but we said that if phi is the minimal polynomial of alpha over K, it's also going to be irreducible and hence the minimal polynomial of alpha over E. The idea was that K is algebraically closed in E. So, I mean, there's nothing in E which is algebraically better than K, only transcendental stuff. And everything in E which is not in K is transcendental. And transcendental stuff won't help you factor algebraic stuff. That wasn't the proof, but that was the idea. So phi is really also the minimal polynomial of alpha over E, not just over K. You added more things, but none of them is algebraic, so it doesn't help you. Okay. So just keep that in mind. Phi is the minimal polynomial of alpha over E. Now alpha is in L, so it's definitely integral over OP. Right? What does it mean for an element to be integral over OP? It means that there should be some polynomial, particularly if there is one, it's going to be the minimal polynomial, monic. All of whose coefficients are in OP. That's kind of the test for being integral over OP, over any ring. You're integral if and only if there is by definition, if there is a polynomial, monic polynomial that vanishes at alpha whose coefficients are in OP. But of course that happens for alpha because alpha is in L. Its minimal polynomial is over K. And K is a subfield of this ring OP. Right? OP is all functions that you can evaluate at little p, constants you can evaluate at little p. So the minimal polynomial of alpha is definitely with coefficients in OP, so alpha is integral. And that's useful for us now because under this assumption that if alpha is nice for p, if it's integral over p, and if the extension is finite and separable, and it is, then the different exponent is bounded by that. It's always at least 0, I kind of added that, but it's bounded by that. That was the last thing I said, like second to last thing I said before. Because the minimal polynomial of alpha is a polynomial over k. So the coefficients are in k, and k is always in every OP. Like for, yeah. Yeah, they're just constant. They are everywhere defined, in particular over p. But, okay, so you have that. I just copy that to the first line here. And then, so, I mean, but now, like, things are simple because, again, alpha is in L. So this derivative, I don't know what this derivative is. It depends on alpha. But, whatever it is, it's in L. Like, you just do derivatives. You just multiply by, like, numbers. X to the n is n times x to the minus 1, so forth. You get something in L, and it's non-zero also, right? This derivative evaluated alpha is non-zero. Why? Yeah, separable, exactly. Because otherwise it would be separable. I mean, we know the extension is not separable. It's a finite extension over a finite field. It's always separable, which is equivalent to saying that the derivative of the minimal polynomial has no multiple root, which is the same thing as saying that the second derivative is not, that doesn't vanish on anything, any root of the original phi. So it's non-zero. And so I know what this thing is. I mean, I know it's 0. I mean, we just said that this is a constant, an element in L. It's not the 0 element. And a non-zero constant element is just a unit. It's kind of invertible. 5 is 1 over, like, the inverse of 5 is 1 over 5 inverse. So the valuation is 0, right? So actually the different is 0 because it's bounded by zeros on both sides. And if you remember, the corollary from Dedekind and different theorem tells you that the ramification index is then 1. And that's what we wanted to prove. Okay, so now we can talk about Kummer extensions. So what is a Kummer extension? Essentially, this is more or less saying all cyclic extensions for which the extension degree is co-prime to the characteristic. That's kind of, you look at all cyclic extension, I mean, it's a very natural question to ask. Regardless of function field, generally, I mean, here I'm going to talk about function field, but generally speaking, a Kummer extension is just, all cyclic extensions, but it's not quite true. There is an asterisk which requires you, otherwise you look at something else, that requires the the characteristic to be co-prime to the extension. If it's not co-prime, for example, if it's the same as the characteristic, it's called an Artin-Schreier extension. And generally speaking, it's kind of, in a sense, kind of a mix of those. But I'm going to talk about Kummer extensions now. So, for our particular purposes, let's say that E over K is a function field. Now, I'm sometimes going to ignore sentences like that, where K contains a primitive nth root of unity. So don't worry about that. It's only used in order to get something about the Galois group, but I don't need the Galois group. So it's written there, and I'm going to, you think of it in another color, and I'm going to read it in another color. Okay, so, but generally speaking, you have a function field, K is the constant field, of course, of F, okay. Yeah, so take a number n, at least 1, like I want to actually have, this is going to be the degree extension. So think of an n, which is co-prime to the characteristic P. And let's suppose that there is an element in E. In a sense, you want to extend E by taking a root, an nth root of U. That's what you want to do. So take this U that you want to take its root. This is going to be U. And assume that, I want to take its nth root, so I don't want to kind of fly. So I'm going to assume that it's not a diff root of anything that's already in E. Right? I want to take like a primitive nth root, not like something which is n over diff root, because, so what I'm saying is that let's assume that U is not a power of some other element in U for any power that divides the n that I care about. Then what I'm saying, or what I'm defining here is that, this function, this field, which is obtained by adjoining y to this field, where y is the solution to this equation, or generally, you take that modding by this relation, such an extension is called a Kummer extension. So again, a Kummer extension, it's very simple. I kind of messed it up a little bit. A Kummer extension tells you, you have an element u in your field, and you want to take its square roots. So maybe you're going to take x plus 1, and you want to take its third root and add it to the new field that you are constructing. Right, so that's going to be like y cubed equal x plus 1. Now, the only little thing that you have to worry about is that, in order for the theorem to hold, and actually in order for definition to be precise, is that your u shouldn't be something which is already a power of something else in the original field that divides n. So for example, maybe if I want to take a sixth root, I need a non-prime number, a sixth root of some element, I just want to make sure it's not already a second or third root. Fourth power of some element, because what I then should do is take the second or third power, not sixth power. It's kind of I want kind of a primitive element in a sense. So that's just the name. That's called a Kummer extension. So whenever you do that, whenever the extension is kind of quite simple, right? It's like only y to the n equals u. It's not like a mix of y's and u's and whatever. Then I call it a Kummer extension. And what I didn't do, and I told you that you may want to see, but it's not crucial, is that there are several simple things you can say about this extension. So first of all, as you expect, that's actually easy. This is the minimal polynomial of y over e because of the assumption about d. So the polynomial that you use to extend it is actually the minimal polynomial. That's the right number. The extension is not always Galois. I don't care about Galois in this talk in this lecture today, but is not Galois unless what I kind of read in green, I don't know, gray, like the color. So if K does contain a primitive and fruit of unity, then it is going to be a Galois extension. It's like when you add a third square root of 2, then you need, you need the right complex numbers in order to keep it normal. So anyhow, don't worry about that. But if you like Galois theory, just know that once you add the primitive root, this is also going to be Galois. I'm not going to use it. And if you care about Galois, then you know that once you do that, then this Galois group is cyclic. And it's really kind of the operation, kind of the automorphism group is determined by what you do to y, and what you should do to y is multiplied by this zeta. If this is zeta, I don't know what this zeta is. Anyhow, don't worry about this too. That's only if you want to, if you like Galois. So, but that's the definition of the Kummer extension. And what I claim is that we completely understand Kummer extensions. Okay, like in terms of function field, like the genus, the ramification index, the different exponent. So in what sense? So let's say that you're looking at a Kummer extension, and just let me remind you the letters. That's what you have, so that you remember who is y and who is u. Then this is the theorem that we're going to prove. It's not trivial, but let's do it. It tells you that if you take a little p and a capital P above it, in the bigger function field, right? So maybe I should also add that f is e y, just so that you'll remember the letters. Then I can tell you what is the ramification index and different exponent and everything using this little notation. So I'm going to denote by R sub p the greatest common divisor of the degree extension, and the valuation of u, that particular element you chose to take its root, like the valuation of p of that element. So you should think of it as very simple. I mean, you know n, I mean, you definitely know n, and you can kind of easily compute that. So you definitely know RP. And the one thing I need to tell you about GCDs, which you know, but you don't know, is that the GCD of n and 0 is n. Okay, I mean, don't be embarrassed if you're surprised. So the GCD of n and 0 is n. Okay, so it's going to come up, and then you think it should be like 1 or something, or you might say even 0, which doesn't make any sense, by the way, because it's at least 1. So the GCD of n and every multiple of n is n, in particular 0. Okay, that's the one thing you should take out of this. Last time, I mean, I didn't understand why people don't understand me, and then I understood that that's the missing part. Like, so I'm just saying that. Don't be ashamed. Okay, so with this number, which always divides n, of course. And by the way, note that it's very simple when n is prime. Like it has two options, n or 1. So when you take extensions whose nth, the degree extension is prime, things are getting even simpler. But generally speaking, then what we are going to prove is that the ramification index is always n over rp, r little p. In particular, you see, it doesn't actually depend on capital P, only on little p. So all prime divisors above little p have the same ramification index. We kind of know that because it's a Galois extension that happens, but And the difference is one shy from that. Okay? So it's like you can see some dedicant have been applied here. And moreover, good things happen. So L is the constant field. So like generally speaking, when you extend things, this is going. I mean, F may have more constants than E. So I usually call this constant field L, and E is constant field K, and I really want them to be the same, and they are the same. No, they are not the same. So there is an if. Sorry, there is a little if here. So if they are the same, there is another theorem after that we are going to kind of encapsulate and make it more pretty. But if they are the same, no. If I'm going to denote by L the constant field of F, then I have a nice formula for the genus of the larger field of F. And that formula, you see, I mean, you don't have to worry about anything. What you can see is that everything here is kind of easy to compute. I mean, L over K, I mean, it's going to be 1 in a second, so don't worry about that. And GE, kind of by induction or something. And the only thing you have to compute is the RPs, which is easy to compute. So that's a very good theorem to have. Good balance. It's quite general, but not too general. So you can say a lot. So let's prove that, and then we'll take a break. But let's prove that. It's kind of long. That's the last long proof that we're going to do. except for next time, like today. Yeah. So we are going to prove this in two extreme cases, and then use the two extreme cases to prove it in general. One time we're going to assume that RP is 1, namely these are co-prime, these N and VP. So I'm going to think of P. I mean, U and N are fixed. So I'm going to look at P's for which these are co-primes, and then when in case when this GCD is actually N, like the maximal it can be, like, no. And then I'm going to combine the two. So we are going to start the proof by assuming that RP is 1. So that's what's written here. This GCD is, maybe I should write it once. So RP is the GCD of N and VP of U. Just in case you want to have a reference to that, even though I'm kind of standing here all the time anyhow. But okay, so let's prove that. So we are going to start by using the kind of that's the easy part. So I'm going to start this one by using the fundamental equality trick. So you know that y to the n is u. So definitely the same valuation of any capital P over little p are going to be the same. But this thing is n times the capital P valuation of y. And this thing, well, u is in the smaller field, so you can write it as the small p valuation times the ramification index. I want to understand the ramification index, so I wrote it like that. And now we assume that RP, which is the GCD between N and VP of U, is 1, right? So this and that are co-prime. So this means that N must divide the ramification index, right? N doesn't divide or has no prime factor with VP of U, so it has to completely divide the ramification index. But the ramification index is at most N, the degree extension, by the fundamental equality, but also by what Kummer did like many years ago. And so really what you have is that the ramification index is exactly N. And I wanted to show that it's actually, if you remember, I wanted to show that it's N over RP, but in our case RP is 1, so it's N over RP. Right? I'm just saying like that's a very simple case because you got away with it easily because the GCD is 1. So just this trick tells you that N divides. This is something we did in example. N divides the VP, N divides the ramification index like easily. No heavy tools, except maybe for the fundamental equality or something before that. What about the different? So we know that if E is 1, the different is 0, but when E is like N, I don't know what the different is generally speaking. But under our assumption, so we are under the assumption that the characteristic P is the co-prime. No, actually, yeah, so that's easy. The characteristic P is co-prime to N, and N, you will just show, is the ramification index, right? And Dedekind theorem tells you that in this case, under the assumption that the ramification is co-prime to the characteristic, the difference is exactly 1 shy away from the ramification index. That was the second bullet, like if and only if.
I must assume that y to the n is not y to the 7, it's y to the anything else.
Yeah, exactly. 7 being the yeah, exactly. Good. So now let's consider. So RP equals 1. We are done with. Let's do RP equals n. So again, there are many possible ways things can happen, but these are the two extremes. So let's say that RP is the GCD of n and so this RP is n. The GCD of n and VP of U is n. It's maximally possible. And in this case, if you think about it, I'm going backwards. So if this is n and this is n, I want to prove that this is 1 and this is 0. Right, that's my goal. Right, so that's what's written here. I want to prove that the different exponent is 1 and the ramification index 0 and 1. And also just note that, as I said, because the GCD is n, this means that this is a multiple of n. Could be 0, could be negative, but a multiple of n. It may have poles there, but it's a multiple of n. So let's denote by VP of U, to be L, some L, integer L could be negative times n, just as a notation. Because what I want to do now is kind of, I don't know how to say it, like regularize that. So let's see. So what I want to do, I mean, I know that y to the n is u, But I want to move from y and u to some better versions of them, which are going to be units in the ring I'm going to care about. So what I'm doing is the following. I'm going to take an element t in E, like in the smaller field, whose p valuation is L. Right, you can always take a local parameter and take it to the power L. So you can do that, because the local parameter has valuation 1. So I'm going to use this t in order to kind of normalize y1 and u1. So normalize y and u to y1 and u1. So I'm going to define y1 to be y over t. Again, y is in f, and t is in E, but everything is in f now. And u1, that's actually everything here is in E. It's u, which is in E, over t to the n, which is also in E. Okay, so why am I doing that? I mean, it's not clear from the get-going, but why am I doing that? So first of all, we know that y to the n is u. I'm claiming that y1 to the n, I'm going to explain, but y1 to the n is u1, so you have the same relation. Just, that's what I want to say first. So indeed, y1 to the n, I mean, y1 is this t inverse u, t inverse y, right? So it's t to the minus n, y to the n. By t to the minus n, y to the n is u. So t to the minus n u was defined to be u1. Just I kind of normalized them correctly. And so again, by the usual tricks that we have, you know that, well, y1 to the n is the same as u1. That's the same element. So their valuations are the same at capital P above little p. But on one hand, this is n times the valuation of y1. On the other hand, what is this thing? So u1 is u normalized. And again, everything on this side happens in E. So you can pull away the ramification index and consider the valuation over little p. So I did that here, and I also kind of split t to the minus n and u. Right? So this is the up to this ramification index is v small p of u minus n times, I took the minus n, v of small p of t. But that's 0. Right? I mean, I chose that because vp of u is L times n. That's how we was here somewhere. Vp of u was, L was defined to be this number. And Vp of t was, again, t was chosen to be an element with v small p equal L. So this is also L times n, so it's ln minus ln, which is 0. So this means that, this thing is 0, right? N is not 0. So Vp of y1 is 0. So what I really wanted to say is that y1 is a unit of O capital P. So y1 has a valuation 0, and therefore also u1, by the way, because the valuations of them differ by a factor of n. So if one of them is 0, the other is also 0.
Why did you, what would happen if you wouldn't normalize?
No, yeah, but it will come now. So yeah. So I just normalized. I really wanted them to be. I wanted y1 to be. You'll see in a second why. But I wanted y1 to be like unit over O capital P. But still, I wanted also u1, and I wanted them to have the same like minimal polynomial, the same relation between them. So that to the n is that. Exactly. And why? So that comes now. So just as a recap, so far we kind of had this relation and they are units. And the point is, I don't know why I wrote so much. It's so obvious. Like all of this, I read it today. I don't understand why I wrote it. But what I'm saying here is that, as I said before, because the relations about d and n and so forth, the minimal polynomial of y is t to the n minus u, right? That's how you extended it. And what I'm saying here, with many words for no reason, is that that's the same minimal polynomial of y1. Because you can just multiply by t and it's an element in E and it doesn't matter. But I don't know, I chose to write a lot of things about that, but it's just kind of obvious. It couldn't be less, it couldn't be more, so it has to be the same. And to your question, we conclude here that y1 is actually integral over OP. Not y, maybe, but y1. Why? What's the reason for that? Is because y1, this is its minimal polynomial, right? T to the n minus u1. And u1, because of what we did, is integral over OP, because its small p valuation is 0. So in all of the extensions, it's also going to be 0, because it's the ramification index times that. If you are a unit downstairs, you're a unit upstairs. Right, because the valuation is only multiplied by something, by the ramification index. So if it's 0 at the bottom, it's going to be 0 at the top for every capital P over little p. So that's what I care about. Because that U1 is in the integral closure of O little p, Y1 is, because of that, Y1 is in the integral closure of O little p. It's integral over O little p. That's what's written here. And as I said, I mean, Y1 also generates F using E, because the only difference is like a T, which is already in E, so it doesn't matter. And again, F over E is separable, finite, generated by Y1. Y1 is integral, so we can use this theorem. Again, very important theorem, just the bound. So the different exponent is bounded by the capital P valuation of the derivative of psi. Now I know psi, it's not like a weird, this is psi, I'm going to find the derivative in a second, but the derivative of psi at Y1. And recall, I want to prove that this different exponent is 0, in this case. So I have a bound on that. When you want to prove that it's 0, the bound is enough, because
Is that okay, you need to do the step with the Y1 so that
U1 will be, no, I want U1 to be in OP, so that indeed there is a minimal polynomial with monic with coefficients in OP, such that Y1 is a root of it. This guarantees that Y1 is an integral element of OP.
so you want one to be
Right. That's what I really wanted, yeah. Y1, yeah, I cared less about it. I just wanted to also generate the same extension and to have the same relation, so I normalized correctly, but I really care about U1, not.
just like find that make them evaluate to 0.
Yeah,
So that's
by
how-
some monic polynomial in coefficients in OP.
Yeah.
Exactly. So, okay, so I wrote it upstairs here. So we have the different exponent is bounded by that. But now again, we know what psi is. Psi is just, t to the n minus something, when you, minus a constant. So when you differentiate, you get n times t to the n minus 1. The constant goes away. It was u1, I think, or something, but it goes away. And when you evaluate it at y1, because that's what you should do in order to apply the theorem, then you get, right, n times y1 to the n minus 1, okay? But what you really want to do is to evaluate that function at capital P. But that function evaluated, okay, so I'm taking it back. I do want y1 to, okay. So the evaluation of capital P at this derivative, right, so this n doesn't matter, it's just a constant. So the evaluation doesn't care about multiplicative constants. So it's n minus 1 times the evaluation of y1 at capital P. And again, I take it back. I do want y1 to be a unit here, because then this means that this is 0. I needed y1 to be a unit in order to apply the theorem, and I want u1, so I needed u1 to be a unit to apply the theorem, and I need y1 to be a unit so that this would be 0. But that just happens by itself. I mean, once you normalize u1, you have to normalize y1 accordingly.
So the relation, so the half of the relation is that they normalize together.
Yeah, right. Yeah, otherwise it wouldn't have worked.
It's like
Right. I can't, yeah, I normalize one, the other one is automatically normalized, and I have to hope that both of them will be 0. Yeah, exactly.
It's the half.
Yeah, so right, so the previous, like, seemingly just technical part is really important, actually. The fact that it works is important. Right, and anyhow, this was, I mean, remember the different exponent is bounded by that, which is 0, so it's 0. And then the ramification index is 1 by the decant. Good. So maybe we'll take a break now, and after the break, we're going to see like how they are fit together in order to do the general case. Yeah. Okay, so let's continue. So far we proved this theorem for the case where RP is 1 and the case where RP is n. And now I want to do the general case. Okay, nice, I think. So in the general case, what we are going to do is, now I don't know what's the ramification, what RP and N is, but I can always divide N by RP. That's the GCD of N with something. So I'm going to define kind of a middle function, y0. Y0 is going to be y to the N over RP, something. And I'm going to extend E by y0. But anyhow, let's consider this intermediate field. And you need to slightly verify what I'm saying, but that's kind of obvious. So what I'm claiming is that T to the RP minus U, I mean the relation between y0 and U. T to the RP minus U is the minimal polynomial of y0 over E. Right? Because if you take this to the RP, you kind of get, y to the N, which is U, equals y0 to the RP. Just take the power of RP on both sides here. So y0 to the RP is U. Anyhow, so you have this, you just take the highest power you can. Okay, so you have this thing, and now if you consider every little p and capital P above it, then below under this capital P you have some prime divisor above little. What we are going to do is we are going to apply the two extreme cases that we had, but I'm going to always switch notation. So just let me recap what we did. So in the original notation, the degree extension was N. There was this P valuation of U. There was this thing that we care about. And RP was defined to be the GCD of these two. Of N, but don't get attached to the name N because it's going to change. So the degree extension and the P valuation of U. RP was defined like that, the GCD of these two, right? Okay. So in our case now, if I'm going to look at E of y0 over E, so I'm looking at this extension now. So you see the extension degree is RP, it's not N. I'm looking at this extension. In this extension, what's happening is that, again, the extension degree is RP. This is the same number. It's like the same U that you're looking at. So that's the same number. And this number was defined to be the GCD of these two. Like by definition, when I'm going to use what we did, RP was defined the GCD of the degree extension, which unfortunately it's called RP now, and VP of U. But if you think about it, it's exactly RP. Because this RP was the GCD of these two. And so really what's happening is this is already at the GCD of some A and B. And you take again the GCD of that with B, that being B. So when you take the GCD of AB and the GCD of AB and B, it's just the GCD of A and B. Like this. Again, so this is A, this is B. RP is their GCD. This is B. So the GCD of A and B, which is RP, and B, their GCD. I don't remember to say GCD all the time, but you know what I mean? When it's the same thing. You can't GCD anymore. It's like already, you got the GCD right. So anyhow, what I'm saying is that the degree extension is actually this GCD is the degree extension. That's the second case. Other case. Okay, so that's just a recap. I put E equals 1 there. And I use the extreme case in which the one of the extreme cases in which the GCD is actually the largest it can be. Right. And now I want to consider the upper floor, F over E of y0. So in order to do that, I need to kind of compute the VP0 of y0. Now U is going to change and to be y0, right? Because the extension above is, y equals, the extension above is y equals y0 to the RP, right? Because of these two. This is the relation between y and y0. So now U becomes y0 in the upper extension. So I really need to figure out what's the valuation of y0 at the small place p0. So I'm computing that for a second. So how can I compute the valuation of y0? So first of all, again at p0, of course. I mean, looking at this level now. So the p0 valuation of y0, well, I know that y0 to the rp is u, so that's the same. From here, I can infer the valuation of p0 at y0, I mean, times rp. And on the other end, vp of 0 of u, well, I can go down using the ramification index. So it's the ramification index times, because u is an e, is the p valuation of u. And I just proved that this is 1. So this is just the valuation of u at small p. So that's the answer. This thing is vp of u divided by rp. Again, I really want to do the same thing, but I'm not going to take a root of u anymore. I'm taking an rp root of y0. So I need to compute this number here. So that's what I did here. And that's the picture now. So now the degree extension is n over. But the GCD of these two, I mean, is rp. And you divide both of them by rp, I mean, to get these two numbers. And then you ask for the GCD. So it's 1. Right? If you have two numbers, a and b, this is a is n and b. Anyhow, is n over rp. And so overall, this thing is indeed n over rp as we wanted. It's the product of these e's. Right, I'm going to skip the different. I also don't think I ever put it here. I forgot it.
Just want to understand, so the reason all of this reduction to the stickers work is because the structure of the curve, right?
Yeah, exactly.
And then in fact, you can divide it by.
Right. It's not every curve that you can do that. Just because it's like y to the n equals u. And then in the extensions, it looks also like that. Y to the n over rp equals something else.
Yeah,
Right. Right. Exactly. So he really heavily used the Kummer kind of type extension. And now, so if you remember, that's what we wanted to prove. We wanted to prove that E is 1, D is 0. No. We wanted to prove that this is E, this is D. I proved the E. I'm not going to prove the D. It's kind of implied by dedicand, essentially. And the gene is just a calculation, really. I'm just going to skip it, maybe, because it's just like plugging things inside. I mean, you just plug it into a homogeneous formula. Once that you know the D's, you just plug them in, and that's it. It's really just like moving around like things. So there's nothing there. Just a calculation, really. So that's what we did. And you see, just calculation. Don't worry about that. It's annoying calculation, it's calculation. Okay. But as a corollary, and that's what I meant, and I think I'm going to skip the proof so that we can do things, but maybe I'll prove it in the video because it is important to see that. Here is a corollary that, I mean, what I like about this previous theorem is that it gives you E and D, right? E and D for quite a general extension. So once you have y to the n equals u, under some conditions, you are happy. What happy means? You know the genus given that L equals k, or maybe given that you know L over k, and that's it really. The only annoying thing is that you don't know that L equals k, and that you kind of by yourself have to check that there is no this W whose diff power is u. It's something annoying to check, like computationally. So I want to remove both of these assumptions by one assumption that's easy to check, which implies both. I mean, also equivalent, by the way, I think. But so here is that's the corollary out of it. It's not so hard, but maybe I'm going to skip it. So it tells you again. Let's say that you have a function field f, which you obtained by adjoining some n fruit of a given element u. So y to the n equals u, as before. But you do need still to assume that p is a co-prime to n. And you don't have to assume that k contains a primitive n root of unity. It's like the same thing. You can ignore it. Don't worry about that. It's only to make sure that it's Galois, but it's not important. But this is the one assumption that I do care about. That's the one assumption that replaces the two assumptions from before. Like it replaces the assumption about the W, and it guarantees that L equals K. That's what I mean. So the assumption is that there is some prime divisor at E, not necessarily rational, by the way, any prime divisor, whose such that that particular U that you're kind of extending going to F has Q valuation which is co-prime to N. Once you have that, I mean, you know N, you know U, you just need to find a little Q for which this holds. Once you have that, then you know automatically that there is no W such W to the D is U. It's not completely obvious, but you can. That's the proof of that. And L equals K. That's a proof. So it kind of simplifies the checks that we have to do. Right. Yeah, exactly. You just need one. And the proof is kind of nice actually, but let me not do it now. I'm going to put it in the video, but okay, we have to kind of hurry up a little bit, so I'm just not going to do it. But it's kind of easy, but not trivial. So, but that's what we are going to do in the examples now. And then, if you want, you can look at out of it. You can take two corollaries. Like one of them, what happens? Like obvious corollaries, completely obvious given what we did. Like just instantiations. What happens, for example, when you look at y squared equal an irreducible polynomial? So very simple case. We talked about yn equals any rational function, u. Here it's just y squared equals a irreducible polynomial. Then here you have some minor conditions, assuming that k has odd characteristic, so it will be co-prime to 2, the degree extension. Then I know everything I want to know. Essentially, I know the genus, which is nice. It's an easy calculation. I'm not going to do it. You can look at it if you want, but it's like completely obvious. Just plug and play. And more generally, when you look at y to the n equals not just u, but when if you kind of look at it closer and you factor u to its rational reducible components in the numerator and denominator, that's what appeared in the examples that I did. If you saw them, then you can break down the requirements from the. I'm not going to use it, but just generally, you can break down the requirements that you have there to give you that like more easily verify the properties that you need to verify in order to apply the theorem. But don't worry about that. We're not going to use that. But I think it's kind of obvious also. It's like just plug and play. Yeah, and that's it. Yeah, that's it. That's all I want to say about Kummer extensions. Any questions?